The title of this podcast is The Development of Fuel Cell Batteries and Its Sustainable Future. The landscape of electrochemical fuel cell battery technologies represents a critical frontier in sustainable energy solutions, offering promising alternatives to fossil fuel and conventional battery-based power systems. As global industries intensify their pursuit of clean energy technologies, fuel cells have emerged as a sophisticated and versatile energy conversion technology with potential applications spanning transportation, stationary power generation, and portable electronics. 1. Market share of fuel cell technologies. The market for fuel cell technologies has been experiencing significant growth, driven by increasing environmental concerns, governmental support for clean energy initiatives, and technological advancements that have improved efficiency and reduced production costs. The global fuel cell market size was estimated at $7.35 billion in 2023 and is expected to grow at a compound annual growth rate CAGR of 27.1% from 2024 to 2030. The current market is dominated by several key fuel cell technologies, with proton exchange membrane fuel cells (PEMFC) leading the way, particularly in automotive and portable applications. As of 2023, PEMFCs account for approximately 60% of the global fuel cell market, with an estimated market value of over $2.5 billion. Solid oxide fuel cells (SOFC) represent another significant segment, capturing around 25% of the market and showing particular promise in stationary power generation and industrial applications. Phosphoric acid fuel cells (PAFC) and molten carbonate fuel cells (MCFC) occupy smaller but still important market niches, primarily in large-scale power generation and industrial cogeneration projects. Alkaline fuel cells (AFCs) and direct methanol fuel cells (DMFCs) hold a market share of less than 5%. Each technology offers unique advantages and challenges, with ongoing research and development focusing on improving overall performance, reducing costs, and expanding potential applications across various sectors. The features of different fuel cell technology are compared in the table from Rotex Technologies website. 2. Advantages and disadvantages of fuel cell batteries. Advantages. Environmental friendliness. Fuel cells produce electricity through an electrochemical reaction, eliminating the need for combustion and reducing emissions of greenhouse gases and pollutants compared to traditional fossil fuel-based power generation. When hydrogen is used as the fuel source, the only byproducts are water and heat, resulting in zero emissions. High efficiency. Fuel cells are highly efficient in converting fuel energy into electricity. Depending on the type of fuel cell, efficiencies can range from 40% to over 60%. Significantly higher than conventional combustion-based technologies. Distributed generation. Fuel cells enable distributed generation, meaning they can be installed at or near the point of use. This decentralized approach reduces transmission and distribution losses associated with centralized power generation, resulting in higher overall energy efficiency. Quiet operation. The absence of moving parts and the electrochemical nature of the energy conversion process contribute to their silent operation, making them suitable for applications where noise reduction is important. Cogeneration capabilities. Certain types of fuel cells, such as solid oxide fuel cells (SOFCs) and molten carbonate fuel cells (MCFCs), can operate at high temperatures and utilize waste heat for cogeneration, e.g., in nuclear or thermal power plant. This allows for the simultaneous production of electricity and useful heat, increasing overall system efficiency and providing opportunities for combined heat and power (CHP) applications. Long duration and continuous operation. Fuel cells can operate continuously for extended periods, making them suitable for applications requiring long-duration power supply or backup power. Scalability. Fuel cells offer scalability, meaning they can be used for various power requirements, from small portable applications to large-scale stationary power generation. Disadvantages. High cost. The cost of fuel cells is relatively high, which is a major factor limiting their widespread adoption. The materials used in fuel cells, such as precious metal catalysts, proton exchange membranes, and gas diffusion layers, are expensive. Taking PMFC as example, the proton exchange membranes, gas diffusion layers, bipolar plates, and most particularly the precious metal catalysts make up around 70% of a PEMF's cost. Hydrogen infrastructure. The lack of a widespread hydrogen infrastructure is another significant challenge for fuel cells. Hydrogen production, storage, and transportation require significant investment and infrastructure development. Without a convenient and affordable hydrogen supply, the use of fuel cells in transportation and other applications may be limited. Fuel purity requirements. Some fuel cells, such as PEMFs, require high-purity hydrogen to operate effectively. This requires additional purification processes, which can increase the cost and complexity of the fuel cell system. Durability and reliability. Although fuel cells have made significant progress in terms of durability, there are still some concerns about their long-term reliability, especially in harsh operating conditions. The performance of fuel cells may degrade over time due to factors such as membrane degradation, catalyst poisoning, and electrode corrosion. Slow startup time for some types. While PEMFs have relatively fast startup times, other types of fuel cells, such as SOFCs, may have slower startup times due to their high operating temperatures. This can limit their use in applications where rapid startup is required. 3. Cost to build fuel cell batteries. The cost of building a fuel cell depends on its application and the type of fuel cell technology. For automotive applications, PEM fuel cells are expected to be the cheapest available, with an estimated cost of around $50 per kW for an 80 kilowatts unit, based on a volume production of around 500,000 each year. However, for stationary applications including domestic heat and power generation and larger-scale power generation, the system demands are more stringent and costs are higher. Fuel cell stacks in the capacity range of 110 kW for domestic systems built from either PEM fuel cells or SOFCs cost around $750 per kW. But these units require significant additional equipment, pushing the unit cost for a complete installation to $1,500 to $2,000 per kW. Larger stationary applications, generally for both heat and power, can be met by large phosphoric acid fuel cell PAFC installations or large molten carbonate fuel cell MCFC installations. For an installation around 1 megawatt, the cost is easily to be around $4,000 per kW. 4. Maintenance and circular economy of fuel cell batteries. Maintenance and end-of-life considerations represent another crucial aspect of fuel cell technology assessment. Typical fuel cell systems require periodic maintenance. The maintenance requirements may include checking and replacing membrane, catalyst cleaning, maintaining the proper levels of fuel and coolant, and monitoring the performance of the fuel cell stack. The average lifespan of a fuel cell stack ranges from 5,000 to 20,000 operating hours, depending on the specific technology and operating conditions. At the end of their life, fuel cells can be recycled or disposed of properly. The development of a circular economy for fuel cells can help to reduce the environmental impact and cost of fuel cell systems. This can involve the recycling and reuse of critical materials such as platinum catalysts and rare earth elements used in fuel cell construction. Current recycling technologies can recover approximately 80 to 90% of platinum from spent fuel cell stacks, with ongoing research aimed at improving recovery rates and developing more efficient recycling methodologies. In circular economy, it also considers the development of sustainable production and consumption models. For example, the use of renewable energy sources to produce hydrogen can help to reduce the carbon footprint of fuel cell systems. In addition, the proper disposal of fuel cells is important to prevent environmental pollution. 5. Challenges for scaling up fuel cell technologies. The scaling up of fuel cell technologies faces multiple challenges that require coordinated efforts from researchers, industry stakeholders, and policymakers. Technical challenges include improving durability, reducing catalyst costs, and developing more efficient hydrogen production and storage methods. Cost reduction. One of the main challenges for scaling up fuel cell technologies is the need to reduce their cost. This requires significant research and development efforts to improve the performance and durability of fuel cells, as well as to reduce the cost of materials and manufacturing processes. Hydrogen infrastructure development. The lack of a widespread hydrogen infrastructure is a major barrier to the large-scale adoption of fuel cells. This requires significant investment in hydrogen production, storage, and transportation infrastructure, as well as the development of standards and regulations for hydrogen safety. Fuel cell durability and reliability. Improving the durability and reliability of fuel cells is essential for their widespread use in various applications. This requires further research and development to address issues such as membrane degradation, catalyst poisoning, and electrode corrosion. System integration and optimization. Fuel cell systems need to be integrated with other components such as fuel storage, power electronics, and control systems to ensure their efficient and reliable operation. This requires the development of advanced system integration and optimization techniques to improve the overall performance and cost-effectiveness of fuel cell systems. Market acceptance and public awareness. The lack of market acceptance and public awareness of fuel cell technologies is another challenge for their scaling up. This requires education and outreach efforts to increase public understanding of the benefits and limitations of fuel cells, as well as to address concerns about their safety and reliability. The global hydrogen economy is projected to require investments of over $150 billion by 2030 to develop the necessary infrastructure and production capabilities. Government policies and incentives will play a crucial role in supporting this transition, with countries like Japan, Germany, and the United States leading in fuel cell technology development and implementation. The automotive sector remains a primary driver of technological innovation, with major manufacturers investing heavily in fuel cell electric vehicle FCEV technologies and infrastructure development. 6. Conclusion. The fuel cell batteries offer a diverse range of technologies with varying market shares, advantages, and disadvantages. The cost to build fuel cell systems varies widely, with some technologies being more affordable than others. Maintenance requirements and end-of-life management present unique challenges for each technology, but all contribute to a circular economy through material recycling. Scaling up fuel cell technologies will require advances in material science, cost reductions, and the development of more efficient manufacturing and recycling processes. Despite these challenges, fuel cell batteries hold great potential for providing sustainable and efficient energy solutions in a variety of applications.